Another one, the PG rule, either 2 or 1, that case, will actually relate if you have a CL at, say, Mach number 0. At what angle of attack it will get a CMCL at another Mach number? This is another rule.
Okay.
So each of you can give one rule. You can actually study one of these rules.
Okay.
And although it's not in our portion, I mean, it's not in our syllabus actually, BTech syllabus, but it is there in GATE syllabus. Like, I asked the students to learn this. You're 2016 batch student. Remember, one fellow got GATE rank 1 from that, Bharat, his group. Okay, because they had taken only elective. So I asked them to, all those who took the elective, to give a presentation on this. And I don't know whether it's luck or whatever. They got a question on this in GATE. All of them did it correctly without any issues. Okay, it is good to know. So can you take that responsibility of teaching the class what it is tomorrow?
So tomorrow I will.
It is not a big thing. It is pretty easy. Okay.
Yeah, but I will do the.
You do one. Vignesh can do one.
Okay.
Vignesh, tomorrow second hour, or no? Tomorrow shall you have first or second hour? First and second hour, or first and fourth hour? What will you have? Sanjay.
First and second hour is fine.
Okay, good. And what about Monday? Do we have a class on Monday?
Sir, I don't think so. We have exams from Tuesday.
Yeah.
Yes, sir. But Monday, I'm not sure if it is working.
Oh, Monday is working, but whether it's working for your class, I'm not sure. I will check. Okay. Usually we work. Okay. Yeah. Usually we work. Unless there's an exam, we'll work. When does your exam end? Last exam. It starts on 7th.
Yes, 14th, sir.
8th and 14th. So, okay. So 7th to 14th, one whole week plus 1 day.
Yes.
You'll be free. I'll check whether. No, I don't have to check. For years together, we have been doing it this way. We can have a class on Monday morning. Okay, not an issue. I don't think anyone will object. Okay, because other final years will have, I understand, but you don't have an exam on that day, correct? So we can have.
Excuse me, sir. Sir, actually, tomorrow I don't think I'll do.
Hello? Hello?
Sir,
Hello?
Sir, tomorrow morning I don't think I'll be able to come to class. I have a doctor's appointment.
Okay, so Vignesh, can you give?
Yes, sir, we will work together, sir, but
tomorrow you cannot give. Okay, no problem, no problem.
Sir, we will work together today, but
no.
Tomorrow.
But tomorrow?
Tomorrow, someone from our group will give, sir.
Someone from your group will give.
Yeah, sir.
Yeah. That's okay. That's okay. Vignesh, you or Sandita or Superman, someone.
Yes, sir. Okay, sir.
And discuss. Okay, I promise you, if you it won't be difficult. If you have difficulties, don't worry. Just present. We'll keep correcting. It's not no marks for this. Okay.
Yes,
just
okay.
Knowledge sharing. That's all.
Okay, sir.
So mistakes are welcome. In fact, it will clarify my doubts also. Okay.
Okay, sir.
PG rule, Franklin Lloyd rule 1 and rule 2.
Okay, sir.
And you choose one person who is not in your group.
So whoever is willing.
Not willing, not for this. This is. We can work with you, but they have to give a different presentation. So, but I'm giving you the liberty of choosing someone. They may not work with you. Sanjay Raghavendra or Sanjay Raghavendra?
Sanjay SS, sir.
SS is overloaded with a lot of things. Right? Sanjay Raghavendra is okay?
Okay, sir.
Where is he? SR Sanjay Raghavendra? Sami Vasana. Sanjay Raghavendra, don't hide. Are you present today? He's gone into hiding. He's not there. He's not present today. Sorry. Okay. Sandita is there? Yeah, she's there. So hey, Sanjay Raghavendra is there. Come on, speak up, Sanjay. Sanjay Raghavendra. Reply to your conversation. I'm not able to respond. Sort. Okay. But can you give a presentation tomorrow? That's the question. You can chat. Do you have a mic to speak? You can type, you can chat. Sanjay. Can you please choose? Can you name another person, Sanjay Raghavendra? You choose. I will ask that person. Yeah. Just tell one more person in your class. Whoever you feel.
Sir, you're asking me or Sanjay, sir?
Sanjay Raghavendra, let him choose one person. Raghu, yes. That decides it. Where's Raghu? Raghu also absent. Hey,
Yes,
Raghu.
sir.
Where is Raghu? Raghu.
Sir, yes.
Yeah. Okay, so here there is one more rule. Okay.
Sir, actually tomorrow I will not be able to do, sir. I'm not.
Okay, yeah. Do it on Monday. Okay. So tomorrow, what happens? Why can't you present?
Sir, actually I'm going out tomorrow.
But you'll be back on Monday, no?
Yes, sir.
So Monday you present. No problem. This rule is called Goethert rule. Goethert. Okay. It is refinement of this PG rule. So you should know the PG rules and then work on Goethert rule. So tomorrow they will give the presentation. You can get from their group what are those PG rules if you don't attend. Okay. If you'll be attending, well, you can hear out what this PG rule is, or you can make your own investigation. Then on Monday, you tell the class what is this Goethert rule. Goethert, Goethert rule. Okay.
Okay, sir.
So you can actually apply this to 3D bodies in axisymmetric flow also. Axisymmetric flow. That is the advantage of Goethert rule. Whereas this the other PG rules are applicable only to airfoils, infinite wings.
Yes.
So that is the advantage of Goethert rule. So you'll be actually, you'll be on the top of the rung when you present this. It's a refinement of this PG rules later on. Okay. So if you know these three, you'll be knowing something a little bit more. Okay, as this course is a bit strange, I will now, and it's wing design time. So I will just elucidate a little bit more on the supercritical airfoil. Quite a few of you may know these already, but I am doing this for the benefit of class, the whole class. I think you may not have encountered. Yes, hello.
Yes, sir. Sir, can I ask something?
Yeah, please.
Sir, I also saw that two small concepts like a critical Mach number and drag divergence Mach number in GATE syllabus, but that we didn't learn these concepts as a part of any course. So
okay, yeah, right.
Some
Hold
insight.
on. Okay.
Yes, sir.
I read your mind today, even before you asked. We'll be looking at it now. Okay.
Sure, sir. Sure.
I'll just share my screen.
Okay.
Or did you read my mind? I don't know.
So you planned this topic for today, sir?
Again, you plan to?
No, did you plan this topic for today? Oh, right.
Yeah.
I can see the screen, yes, sir.
Yeah, okay. Right. So this, I'll just go through the development of transonic flow on airfoil. As free stream Mach number increases beyond critical Mach, beyond, okay, beyond critical Mach number. Actually, you can find this detailed explanation in John D. Anderson's compressible fluid flow book. Okay, he has written a book called Compressible Fluid Flow. There you'll find all these pictures. You can find in many other books also, but I am just briefly mentioning these. So okay, now what is critical Mach number? M infinity is M critical. So anywhere in the flow or somewhere in the flow accelerates and Mach number is just equal to 1, which means the maximum Mach number in the flow field is 1. When that is reached, the corresponding free stream Mach number is critical Mach number. Any doubt here?
No, sir.
No, sir. So everyone is clear on that? Vignesh, clear?
Yes, sir.
Raghu, is it clear?
Yes, sir.
Okay.
Can you repeat?
That is the flow there is a Mach number at which the flow becomes the maximum Mach number in the flow. It may be anywhere in the airfoil, anywhere in the flow. Mostly it will be on the airfoil. Okay. Somewhere the maximum Mach number of the flow becomes 1. Maximum Mach number becomes 1. So the flow becomes sonic at a point. So since this is the maximum Mach number, the free stream Mach number will be less than this Mach number, no? Raghu?
Yes, sir.
The free stream Mach number will not be 1, it will be less than 1.
It will be less than, yes.
Yeah, but the flow accelerates, so somewhere Mach number is 1. After that, Mach number is less than 1. Before that also, Mach number is less than 1. Okay, so the Mach number is exactly equal to 1 at some point in the flow. That M infinity at which it becomes like this is known as critical Mach number, M critical. Okay, Raghu, is it clear?
Okay, sir.
You'll have many critical velocity, critical something, but in compressible flow, this is what is meant by critical Mach number. So
Yes.
look at this pictures. I have named them A, B, C, D, E, F, G, and H. Okay. So look at the B. If you increase the critical Mach in M infinity beyond critical Mach number. Now look at the bottom. MA is less than MB is less than MC is less than MD is less than ME is less than MH, MF is less than MG, MH. So which means that the Mach number keeps increasing from MA. That is, MA is critical Mach number. If you don't know what is critical Mach number still, please raise your hands and ask me again. It's very important to understand this. I assume it's clear to everybody. Then if you increase a little bit further, what happens? You get a supersonic pocket on the airfoil. Somewhere there. Usually it's the top surface. So, supersonic pocket means the beauty is there is no shock here. There is isentropic acceleration to supersonic flow inside the pocket and isentropic deceleration after the pocket. So you have a sonic line without having a shock. You see a small pocket where M is greater than 1. Everywhere outside M is less than 1. So this dotted line, the sonic line where M is exactly equal to 1. It differentiates the supersonic pocket. It separates the supersonic pocket from the subsonic flow outside. Clear? Any doubts here?
Sir, so for our aircraft, we have taken Mach number as 0.88, so that will be in this range, no, sir?
You are having supercritical airfoil or what?
No, sir.
So that will be means we don't know. Unless we don't see the critical Mach number is different for different bodies.
Okay,
For very thin and sharp bodies, it may be very near 1, maybe 0.95. But if the body is bluff, it may be as low as 0.5 or 0.6.
Yes, sir. Okay, sir.
So you cannot say for a different body, even the same body at a different angle of attack will have entirely different critical Mach number.
Okay, sir.
So it depends on orientation of the body and the body itself.
Okay, sir.
Okay. So if you increase it beyond B, what will happen? The supersonic pocket becomes larger, but it now terminates in a small shock. Now, this point at which the shock is there, after this the drag starts rising steeply. Drag means I am telling CD naught. This is CD naught becomes now CD naught F, which is frictional, the skin friction drag, plus CD naught W, which is a wave drag. Wave is nothing but shock wave. Due to the shock wave, the drag starts rising. So there will be some free stream Mach number when this happens. That is drag divergence Mach number. Okay. Sanjay, is it clear?
Yes, sir. Clear, sir.
Yeah. Some more. It will become clearer when you go along. So beyond drag divergence, we further increase the free stream Mach number. What will happen? You get a strong shock. So drag will be even more. You further, that is point D. Means the state D. Increase further to E, you get a shock in the lower surface also. You are going to get more drag. You increase further, these shocks, the bottom shock may overtake the top shock, or it may not. Depends on the airfoil and angle of attack. I am taking the situation where the bottom shock is actually overtaking the top shock. Okay, because now things will become more sticky and complicated. Right. When you further increase the Mach number, both these will travel to the trailing edge. You'll get two trailing edge shocks. Remember, up to this point, the free stream Mach number is less than 1. The acceleration is only over the airfoil. Beyond this, when free stream Mach number is more than 1, you will have a bow shock before the airfoil. And the situation is almost frozen. Okay, which when you further increase the Mach number, the situation is almost frozen over the airfoil. The pattern doesn't change much. Okay, so look at this A, B, C, D, E, F, G, H. The point where the shock starts developing is known as drag divergence Mach number. Now, the process, when exactly a shock forms, is a bit nebulous. It is a bit uncertain to define. Okay. When a lot of compression waves start coalescing together, they don't suddenly coalesce. Okay. 2-3 compression waves will start coalescing. If you increase further, more compression waves may become nearer. So this is how a shock develops. Okay, I'll just draw one. So it's a gradual process. What I mean to say is, at some point the shock is strong, but there is no fixed, definite point at which you say, now there's a shock, now there's not a shock. So it's a gradual transition. So when do you say the shock is there? So to avoid that, people have a different definition of drag divergence Mach number. I'm telling you why this drag divergence is happening now. It is because of shock formation. Okay, but what do you exactly call as drag divergence is a little bit different. You define it as You take the CD naught at drag divergence Mach number and CD naught at critical Mach number. When the CD naught at drag divergence Mach number is 2% more than the CD naught at critical Mach number, you say that okay, now this is the drag divergence Mach number. You increase Mach number any further, the drag is going to increase exponentially. I mean, at a very high rate, as shown in the figure. When I say drag here, you appreciate that the CD naught I am talking about, not the CDI, which is induced drag. I am not talking about the induced drag CDI, which is KCl square. Okay, this is only about CD naught. Now CD naught will have two components: the CD naught friction, which is almost constant. The extra drag is due to shock. Drag means, okay, drag coefficient. I should say, drag coefficient is zero lift, to be very, very precise. But I am loosely telling drag because everybody uses the word drag. And this is actually, it is CD naught. So this C is where drag divergence, so this is called MDD. Drag divergence Mach number happens at C. Critical Mach number happens at A. Okay. Now you take the difference in drag. For example, here drag is so much. At C, drag is somewhere here. So this difference, okay, when this becomes 2% of initial CD naught. The CD naught at M critical, okay, this point. Of this point, then you say that free stream Mach number is drag divergence Mach number. Sanjay, it's clear?
Yes, sir. Clear, sir. Sir, this is valid only for supercritical airfoils?
No, any airfoil.
Okay.
I'll tell you what is supercritical airfoil shortly.
Okay.
Anyone else? Is it clear for all those who are present here? Sandita, clear? Dev Sultan, Nandakumar,
Sir, yes, sir, clear, sir.
Rajeshri,
Clear, sir.
Yes, sir.
Aditya,
Clear, sir.
Niveta.
Yes, sir.
Okay. So now we have looked at the variation of CD naught and the definition of drag divergence Mach number. And what is drag divergence actually? Beyond C, you see, it will be actually, it is not even this. It will be very steep. Like this, it will go. So I should actually rub this off. That's why it's called drag divergence. Drag will, increase very suddenly after the drag divergence Mach number. But you see, there's a sweet spot. Why I call it a sweet spot is between critical Mach number and drag divergence Mach number, you have supersonic flow over the airfoil without a shock. Okay. It's a very nice area to fly. You'll get lot of lift with less drag. High efficiency, you can fly very nicely without the drag penalty. Now, commercial aircraft, they want to actually, fly in the sweet spot. Well, if you give me a Mysore Pak, I'll ask for one more. If I finish that, I'll ask for one more. When I cannot eat it for any longer, I'll tell you, please give me 10. I'll put it in stock. I will take it once when I like. So, when you get this sweet spot, you want more and more of it. So, what happens? This is where supercritical airfoils come into picture. Okay. Supercritical airfoils do not affect the critical Mach number. They don't do anything to change the critical Mach number. But they increase the drag divergence Mach number. For example, if a critical Mach number is 0.75 and drag divergence Mach number is 0.78, If you use a critical Mach number, you can still have the critical Mach number as 0.75, but the drag divergence Mach number will be, you can increase to 0.85, 0.86, 0.87. So you'll have more of the good thing. So they move the point C, which is the drag divergence Mach number. Where is the point C here? Something is. This is the point C, drag divergence. So you can have the shock formation at a much later Mach number if you use a supercritical airfoil. So they don't change the critical Mach number, but they increase the drag divergence Mach number. That is the main advantage of using a supercritical airfoil. How do you increase the critical Mach number? For example, 0.75. Now we saw that if you have a wing sweep, leading edge sweep, you can increase the critical Mach number to 0.75 divided by cos of leading edge sweep. If leading edge sweep is 60 degrees, what is cos of 60 degrees? Cos 60 is 1 by root 3, right? Am I right?
Half.
1 by 2.
Half, 1 by 2, 1 by 2. So your critical Mach number will become 0.75 by 1 by 2, which is 1.5. So free stream Mach number may be even supersonic, 1.5. But the airfoil will feel only m cos theta, which is 1.5 into cos 60. So it will feel only 0.75 as the free stream Mach number. Okay. So this is how you can increase the critical Mach number. When you talk of drag divergence, you come to the airfoil. In the airfoil, you look at the airfoil free stream velocity, which is now 0.75. Mach number is 0.75. Even though the free stream may be 1.5, we have a Mach number of, if you have a sweep of 60, free stream velocity may be, free stream Mach number may be 1.5. But the normal Mach number will only be 0.75. That is where the critical flow features will start appearing on the airfoil. Okay, so critical Mach number has nothing to do with drag divergence Mach number. Or sweep. Sweep does not affect the drag divergence Mach number anyway. It only increases the critical Mach number. Whereas supercritical airfoils, they do not change the critical Mach number, but they do increase the drag divergence Mach number. So you can even combine these two and get very good results, especially for transonic flow. So supercritical airfoils, transonic, even if Mach number is 1.2 or 1.3, if the free stream Mach number is then, the wing, the component normal to the wing leading edge can be subsonic. In addition, if you have supercritical airfoil also, you can hit the sweet spot. Okay. So now, okay. Next one, very interestingly, this is, so I have told whatever you need, whatever, the basics are there about supercritical airfoil. Someone trying to contact me.
Sir, I have a doubt, sir.
Yeah, please. Most welcome. Ramanathan,
Yes, sir.
tell me, what is the doubt?
Sir, actually, after sonic line, it is supersonic, no, sir. So, you are telling the sweet spot. That sweet spot is very minute spot, no, sir.
Yes, but it is very important for commercial airliners. If you can make such a small savings, you can translate into a very big design advantage. If you can improve your performance by 2%, you can save millions of dollars per year. That's how they will calculate. Okay. Now you can have it in different ways. You can either see drag is going to be less, no? Ramanathan. Ramanathan, hello?
Sir, can you hear me, sir?
Yeah. Now I can hear you. Tell me.
Yes, sir.
See, if I can fly faster, I will be actually saving fuel for the same range.
Okay, sir.
That is one advantage. Otherwise, I can have the same fuel, but I can have a thicker airfoil.
Yes, sir.
Because I have a thicker airfoil, I can actually reduce my weight, structural weight of wing.
Yes, sir. Yes, sir.
Because I reduce structural weight of wing, I can reduce the fuel I carry.
Yes, sir. Yes, sir.
Because I reduce the fuel, so overall weight will reduce.
Yes,
So
sir.
I don't need such a powerful engine.
Yes, sir.
So although it may look minute, the overall savings is very significant. That is why people are
Yes.
researching on this.
Yes, sir. And this to get this drag divergence Mach number to be higher and higher, it is purely geometry of the airfoil.
Geometry of the airfoil. They start with method of characteristics to do that.
Okay.
Okay. And they saw that this shock is forming only because you see, I'll probably draw another diagram for that.
Okay.
Because you asked the doubt, I have to go a little bit deeper. Okay.
Okay.
Normal airfoil, what will happen? That is normal airfoil. You will have this, sonic line. Inside the sonic line, m is greater than 1, no? So from here, some characteristic will go, it will hit and come back. Oh, you are not exposed to method of characteristic, no? Or are you?
No, we are
Sir.
not.
No, sir. No, sir.
So let's say Mach lines, okay? Right now you tell Mach lines. From this point, another may hit here. It may come. And it may be going like this. What happens here? They try to coalesce these two lines, correct? They get closer.
Yes, sir.
And another may from here, it may hit and it may try to coalesce. Now what happens? When more such things coalesce, you get a small shock here. Yeah, who asked the question? Yes, Ramnathan. Did you ask a question
Yes.
again?
Sir, I think Sanjeev was.
Sanjeev, yeah, tell me. Sanjeev, I think he lost connection. No problem. He'll ask me later. Now in supercritical airfoil, they cleverly design it so that it is flat on the top, relatively flat. It's not exactly flat, okay? When the sonic line develops, let me call this as 1.1, 2, 3. This is 1 prime, 2 prime, 3 prime. See, this characteristic lines do not have meaning in subsonic flow, so they get reflected by the sonic boundary. That is one secret I should tell you. Not a big secret.
Yes, sir.
Yeah. So the 2, when it comes here, it will be almost parallel to the initial line. Okay. Rather, if I extend the airfoil, they won't coalesce here. This is 1 prime, 2 prime, 3 prime. So the shock formation is delayed by the geometry. How to design this? You need to use method of characteristics to start with. Then you can do CFD simulation after that. Okay,
Yes.
Ramanathan? Yeah.
Yes, sir. Got it, sir.
Yeah.
Thank you.
Yeah. So this is how they work. If you increase the angle of attack or something, then they may coalesce. But there, for the flight angle of attack, they make it look like this so that For a higher Mach number, they will coalesce. This is how actually is designed and this is its function. And because of the distribution on the top, will have more load on the top. There will be some effect on the CM graph. So to give the airfoil stability, this one is bent in the rear. Okay, because it will look on the CP curve. If you see that, I don't want to go into how the CP curve will look like. It is going to look complicated. Okay, CP versus X.
Yes.
Well, let's not go into it right now. So, but know
Okay,
that this CP versus X curve, the shape will be favorable for a good moment if you give a small, bend here. That is why it is having the what do you call this? The camber is more at the trailing edge.
yes.
Okay. So much about supercritical airfoils. Now for return to transonic flow, CL will also exhibit some kind of cranky behavior at Mach number equal to 1. As a result of the CD naught increase and CL funny behavior, if you plot CM versus M infinity, now when you do this, dCm by dm is negative, correct? dCm by M infinity is negative here, it is negative here, but near 1 it is positive. This region is where the bottom shock is actually crossing the top shock. I told you, here. The bottom shock crossing the top shock. That is when this kink happens. Then the top shock again overtakes and crosses the bottom shock. Because of this, the result on the moment curve is like this. Okay. When this happens, there is a positive dCm by dm infinity is actually positive. So if you had studied speed stability in flight mechanics, have you studied speed stability? Sanjay, you are my only refuge.
Speed stability or sweep stability?
See, speed stability means how if you increase the speed, okay?
Yes.
How does the moment vary? If it is negative, you can say that the speed stability is there.
Yes, sir. We studied, sir. Yes.
If it is positive, then it's not stable.
Yes,
Okay.
the gradient is negative usually.
Yeah. dCm by dm. This is not dCm by d alpha.
Yes.
Okay. Talking about dCm by dm. This is the Mach number. Here also the same argument will hold good. If you have doubt, later we can have a session to explain this. So in short, what happens is the CM graph, suddenly the CM will increase, so pilots tend to bring it down. So when they increase the speed to cross the sound barrier, this is why a lot of pilots lost their lives. Suddenly when your CM increases, what do you say? It starts pitching up. So what do? The pilot tries to push the stick down so that angle of attack reduces. But when the speed further increases, naturally it is going down. You further move it down, what's going to happen is going to crash. So this is the reason why a lot of people lost their lives before crossing the sonic line, the sonic boom they call it. It was sound barrier was broken. Later people found out how to overcome this. Just hold the stick steady. Okay, let it pitch up. The automatic will pitch down after some Mach number. You hold on steady, nothing will happen. You will come back to normal. So solution was simple, but it was not intuitive. So before it was discovered.
Sir, that is the reason we have trim tabs, no, sir.
No. Trim tabs can be used at any Mach number. not only at this Mach number. Trim tabs, actually what they do is, okay, let
Because
me take
pilot does not
attendance.
hold the stick continuously.
Yeah, I'll tell you what it happens. What it is, okay. Let me take the attendance.
Okay.
You have a class next one. Don't worry, I won't take the next class, but I'm just asking out of curiosity.
Yes, sir, we have.
Okay. What is the class?
We have technical training, sir, CAR. But that's at 11 o'clock.
11 o'clock. Okay. So I can take some time to explain your doubt. One more paint session. Okay. So what were you asking? I got the question now.
Trim tabs.
Trim tab. Okay. So what is the trim tab? You have a you have an airfoil. Then you have a flap. If you want to trim it
Yes.
at a higher velocity, what will happen? So you are going at velocity of 100 meters per second. Okay.
Okay.
Now you want to go to 120 meters per second, the same height. If you go at higher speed, what will happen to thrust? What will happen? Thrust should be increased.
Yes, sir.
So because drag will increase, correct?
Yes.
So thrust should be increased, but is that alone enough? Is everything good once you
No,
increase? What will happen?
sir, we have to maintain lift equal to weight.
Yes, you have to maintain lift is equal to weight. So what do you do?
Increase the angle of attack, sir. Sorry, decrease the angle of attack.
Yeah, decrease the angle of attack. How will you decrease the angle of attack?
Pitching down.
By deploying flap.
How will you pitch down? By deploying this flap.
Yes.
Okay. Deploying the flap. Now we have heard of hinge moments.
Yes, sir.
There's a hinge here at the flap, correct?
Yes, sir.
So now imagine you have a door hinge, okay? You can freely move. What if you have a spring at the door? You have to keep on pushing your hand there to hold the spring, right? If you release your hand, immediately the spring will come back and the door will come back to original position. Correct?
Yes.
So now what happens? Imagine the aerodynamic force is acting on this, like that spring. If you deflect it down or up, whatever, what will happen is this will create the aerodynamic force here. Initially here, when it's at equilibrium, there will be some CP distribution which will be maintaining it. The aerodynamic force may be different, which is, some force may be acting on this fellow, the flap. Now here, if you deflect it down, the angle of attack of this one increases. So the force will be larger. What will it do? It will tend to move it like this. If you want to hold it there, the pilot needs to hold on to the stick so that it will resist this moment caused by the extra lift it's having. Understood, Sanjay?
Yes, sir. Yes, sir.
Yes. Now, can he hold it for 1 hour if he wants to fly at 120 meters per second for 1 hour?
No, sir.
He will become very tired.
Yes.
So you have this trim tab. So if you call this the daddy, this is the son. You have the grandson, which is trim tab. Okay.
Okay, sir.
So this one, what it will do is, because of the tail is deflected, this will again have a small flap of a flap. That is trim tab. Now this will create a moment like this, around this, whereas this will be arranged in such a way that it creates a counter moment. Okay, because the deflection is different, no? So the force will be like this here. Now this moment the effect of this is significant to cancel this hinge moment here. If you have this, if you call this moment as, F, this moment as T, see the center is here. F is very large, the distance is small from this hinge, whereas T, the distance is larger from the hinge, so T can be small. You got it?
Yes, sir.
Yeah. So when the pilot tries to trim, he takes 1 or 2 minutes to find the correct position for this. Where to position this. Then it will be in equilibrium. He doesn't have to worry. This itself will supply the necessary this one. Or it can be done automatically also in some planes. Okay, or the pilot needs to move a small trim lever to find the position for trimming. Now he can take his hands off after that 1 minute. It will keep flying at 120 meters per second very smoothly. What is the penalty? The shape is a bit distorted. So you may have a little bit of drag more. But then, interestingly, the trim tab size is so small, it doesn't affect the lift much. Only the moment around the CG is affected. Moment around the hinge is affected. Even moment around CG is not much affected. It is designed in such a way. So this is the counter hinge moment, trim tab. That is the fun question. So if you counter the hinge moment, the pilot's fatigue will be reduced. Okay, that's all.
Okay, sir. Got it, sir.
I'm not using mathematics. I'm just using some, conceptual understanding for you to understand what it means.
Excuse me, sir.
Yeah.
Sir, actually, if we are going from 100 meter per second to 120 meter per second,
Okay.
we'll be gradually decreasing the angle of attack, sir. So, will we fix this trim tab, or that also will be gradually moving?
No. You'll fix it. After you move it, then you allow the trim tab. You don't. What I mean is, you don't keep trimming it in every 111, 112, 113, 114. Only after it reaches 120, you start trimming.
Oh, okay, sir. So it's something like a lock of the for the.
You can lock it or leave it free. There are two things: stick fixed and stick free are there. No, not only for trim tab, even for the elevator also. The control also has stick fixed and stick free condition. Stick free means naturally it will come to rest at some position where it's equilibrium. So you don't control it. So you don't try to control the velocity at which it is actually flying. That is stick free. Or the angle of attack. But in stick fixed, you are trying to maintain some velocity and angle of attack. Then you are fixing it at that point. Then using the trim tab. In that case, trim tab will be more useful.
Okay, sir.
The stick free condition, trim tab will automatically find its own position.
Oh.
Okay.
Okay, sir. Yeah.
Yeah.
Thank you, sir.
Welcome. Now, Ravana.
Sir, no, even this trim tab will have its own hinge moment.
Yeah, very small moment. Yes, it will have. Now that moment is negligible. Here, no.
Okay.
But
yes, sir,
the
yes.
pilot's control is only this one.
Flap.
Yeah, the pilot controls only flap. The trim tab also will have a small mechanism to control it, but the moment produced by the trim tab around the plane is very minimal. The moment around the flap only counts. I mean the hinge. This hinge.
Yes, sir. Yes, sir.
Yeah. There's a hinge here also, second one. Yeah, agreed. But it's a very small, very minor when compared to the main hinge.
Okay, sir. Sir, but I've just gone to one of the places, sir. So I've seen through the window, but I can't see the trim tab, sir. So
it is some planes use it, some planes don't use it.
Oh, okay.
It is not found throughout the wing. And it may not be there throughout the wing. It may be only on a small span of the wing you can find it.
Okay. Yes.
Like rudder also may have a trim tab. It is not a absolutely necessary contraption, but it's good to have kind of thing. For
Yes.
some large planes, you will find trim tabs. For smaller planes, you may not have trim tabs also. In that case, they use the stick fixed and stick free concepts to alleviate pilot fatigue. Or as another vision told, they may hold a lock it at a particular angle of attack if they want to go ahead. Otherwise, autopilot is there to
Yes,
control.
yes.
If autopilot is there, then that will do the work of the trim tab. As long as the pilot doesn't have to worry, he is good enough. Autopilot will give the necessary input time and again.
Yes.
So it all depends on what the designer wants to have. Okay.
Okay.
Yes. Okay. Any other doubts? So tomorrow we can expect that presentation from Vignesh group. Then we'll have a presentation from Vignesh group. Sandita, Vignesh, Aditya and Super9. One of them can present, up to them. Then one more from PG1 and PG2 they'll give. Gothar 2 will be given by Raghu on Monday.
Sir, is it possible to not have classes on Monday, sir?
If Raghu gives it tomorrow, then we won't have class on Monday. It's possible.
Okay, I will try, sir. Try to.
Raghu is not prepared, then we'll have on Monday for Raghu's. Okay? Okay, Raghu.
Thank you, sir.
Thank you.
Thank you. I'll end the
Thank you.
meeting. Bye. Thanks. Bye.
Thank you, sir.
Thank you.